Log on, tune in, find out. Another good idea from Cambridge.
The next speaker is Andreas Spillner, and again talking about networks.
Okay, can you hear me? Okay. So I have to thank all the previous speakers from this morning session because they did a very nice job explaining what split networks are in particular, so I don't have to do that. And I can jump straight in and start with an example of a split network. It looks quite boxy, a lot of these little parallelograms showing up, so it's from some data set involving species of oak gall wasp, and so it's definitely not tree-like, and I think that's what those split networks are often used for. You get some glimpse of what's in the data. Is it tree-like or not? If there's a lot of boxy things showing up, then well, you probably will have some more analysis to do to check what's behind this boxy appearance, the non-tree-likeness in your data. One thing I would like to point out here is that although it's looking a little bit complicated maybe, and you can't see it because it's, what, 80 text after all, if you really look in closely, then all those labels, they appear on the outside of the network, and that's what's in literature called an outer-labeled network. And on the next slide, I will just briefly show you or remind you of the little pipeline that you could use, or that is usually used, to get this kind of network in the end. So you start with some data, maybe some sequence alignment, and get some distance matrix, and then from the distance matrix you use some method, maybe NeighborNet. There are others as well, but in this case it was NeighborNet that was used, a method by Bryant and Moulton, and it constructs some combinatorial object. Well, it's a simple one, just a circular ordering as we have seen before, and then this circular ordering gives you a set of potential splits by partitions of your set. N choose too many if they're n texter, so in this case it would be 5 choose 2, and then on those potential splits you put weights, and well, you do that in a kind of least square sense, non-negative if possible, based on the distance data that you have given. And in the end, you display those splits in the form of this network, and the lengths of the branches or the edges in the network, they correspond to the weights on that you put on those splits. Some of them might actually disappear, and that's what you want to do, because if you have, say, 200 texts, you don't want to have 200 choose 2 splits in your network. You probably want to have something like linear or slightly superlinear, but not n choose too many. So you hope that many of the splits actually collapse. Okay, but what I'm not talking about today about how to produce or how to replace this, but what I'm talking about is the drawing algorithm, the one that is used and it's implemented in split trees due to Dress and Huson, and some improvements by Philippe and others. But the nice drawings that you get, they are those that come from, say, circular split systems, because then you get those outer labeled nicely planar networks. And what I would like to do today is discuss a little bit what you can do beyond that. And maybe before I get into this, I give a little motivation why I think it could be interesting to explore that a little bit. So if you go through the literature, there are, first of all, other methods, of course, how you can go from the data, especially from a distance matrix, to some split system and then draw it. For example, there's split decomposition that, well, is a little bit old, but on the other hand, it has the potential to produce split systems where you have things that are labeled in the interior that are not outer labeled like the ones that you get from NeighborNet. And so those things do occur, and also this example that we have seen in the beginning, it was some example that involved geographic information. And geographic information, well, those gall wasps, they get carried around because a tree is cut down and then the wood is transferred to some other place in Europe. All those gall wasps, they were living in Europe, so say some oak tree is cut down in Spain and the wood is then transferred to Hungary or whatever. So, I mean, there's definitely some countries lying kind of in between the countries that are involved, say between Spain and Great Britain, there's France, and some interior things do show up in certain situations. And in this talk, I would like to explore a little bit how we can incorporate it into this framework of split networks. So in this slide, I try to get to the underlying combinatorial object that can be used to get split networks that have interior labeled things. That's what we want. But still the network should be planar in the end, so it should have a nice drawing. So I would like to extend the stuff that we can draw in a nice way, as Celine put it, but not necessarily have the restriction that I have to put everything on the outside. So kind of intuitively, a flat split system, that's something that can be drawn nicely by a planar network, is something where you get such a network. Well, okay, that's not very helpful, especially there's some technical problems with those pendant edges sticking out in the middle. I will come to that, back to that later on maybe. You can do it very formally, and Brian Dress did that by bringing up a definition using what's called oriented matrix of rank 3 and da-da-da. I give you a nice picture on the next slide that makes this a little bit easier to digest. But if you do put it formally, then there's immediately the question, can I actually decide if somebody gives me just a list of splits? Is this a nice one? Is this a one where I can have in the end a nice split network? Or is this some nasty beast that I cannot actually display nicely? And I don't know, so that's still open. So, well, what we need to assume is that somebody, well, don't know who, but somebody needs to give us a combinatorial structure, like the circular ordering that you start with for this outer label things. I mean, you do not start with a list of splits there. You start with the circular ordering that you have, and based on that, you actually draw your nice network with the labels on the outside. So now we have to find a replacement for the circular ordering. And for the purpose of this talk, I really made a nice picture of what is called a wiring diagram. Essentially, it generalizes what we've seen as a circular order. The circular order is just the ordering on the left-hand side here, x1, x2, and so on. And then in addition to that, you need some more information. Yeah? There is kind of things that are next to each other, they can swap positions. So what you think of is you have not just one permutation, not just one ordering like in the circular case, but you have a whole sequence of them. And the way to see it is, yeah, you put on a vertical straight line here, then you just keep walking. And every time you walk across one of those dots, two things swap their positions. So you start with this permutation, x1, x2, x3, x4, 5. And then you carry on, it stays the same position, but here it swaps. Now x3 and x4, they swap their positions to get a new permutation. So what you get is a sequence of permutations, not just one as in the circular case, a whole sequence, and this can be combinatorially encoded, and that's what we actually use in the algorithm in our implementation. But drawing it in this way is nice, because then I can just look at the picture. So what is a flat split system? You draw one of those things where you have a sequence of permutations drawn nicely, and then you point at some of the faces in here, and then you look at the things that are below it, like this one, x1, x2 is below it, and x3, x5, and x4 is above it. So this would be the split x1, x2 versus x3, x4 is 5, and for the others as well. So something is flat. If I can draw something like that, then I point at a couple of faces in it, and this is my split system. This is my collection of splits, and if I can have such a representation, then I call it flat. That's a nice, intuitive, and visual way of putting things, at least for this talk. And for circular things, you have a nice regular representation. You just put the circular ordering that we have anyway, and then you see you can just wire things through in this regular way. You start with the one below and go all the way across and continue here. The next one, well, you've already done it once, and then you take it all the way across, and well, it just continues. You can do it for any number of elements, and you always get this nice regular thing. Okay, that's circular. You get also non-circular. I mean, if you only could do circular, that would be a little bit, poor, but we can do non-circular things. And then, well, I don't want to go too much into the details, but essentially what you can think of a circular thing is you map the elements in your tensor set onto a set of points in the plane, but they need to be in convex position. Just put them on a circle, yeah, on the rim of a circle, put them there, they are in nice convex position. But if you drop that condition that they have to be in convex position, just move them arbitrarily in the plane, then still you can represent the splits by just going across, cutting them by straight lines in the plane. You get again a split system. It has again, if there's n tensor, n choose 2 splits in it, and that's what people call an affine split system. Those are usually not circular unless they are in convex position, the points. And by using this nice and old duality going from points to straight lines and back, you can really encode this thing again in such a wiring diagram, have to do it topological, just disturb it a little bit. But let's not go into this detail. But these things, these mappings from the taxa into sets of points in the plane, give you examples of non-circular things that are flat, and they can be used in various ways. And I will give you some examples at the end of my talk. Okay, so we get those things. We get flat split systems with an encoding that might be helpful for drawing these things. So now let's just get quickly through the algorithm how we transform this thing, usually encoded just as a sequence of permutations, into some split network. And the nice thing about this wiring diagram is that I can talk about things that lie, so if the taxa are x1, x2, x3, and so on. So if I take x2, then it's just this little polygonal curve going through here. And if I look at it, I can talk about splits lying below it. For example, if I have x2 going through here, then S3, S4, and S5, no, S3 and S4, they are below it. And S1 and S2 and S5, they are above it. This above belowness is a very nice thing. It's very intuitive. And that's will be helpful in the algorithm, because somehow what we do is we start off with, well, a chain representing the splits in the order in which we encounter them by walking from left to right. So S1, S2, S3, S4, S5. That's the order, that's the initial chain of my split network that I'm going to construct. And then I have to add in those boxy things step by step. And I will show that on the next slide. So that's what we do essentially. That's how we start. All the time we keep this bold path of edges. That's the boundary of the things that we've constructed so far. And in every step we add in another box. And how do we do that? Well, we process the labels, that's x1, x2, x3, x4, x5, and so on, one at a time. And all we have to do is in each phase, so this is what we start with, x1, well, it can be placed already here, but it becomes clearer why if we just carry on a little bit. So suppose we have placed x1 here. Now we want to place x2. We cannot do that immediately. Why not? Because first of all, we have to make sure that on this bold path we have sorted the splits accordingly to this above-belowness thing. Yeah? If you look at this path, then you have to place x2 somewhere on the path, but somehow here you have certain splits. This is x5, s4, and so on. Some of them are below x2, some of them are above x2. But now they are not sorted in this like above, 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 below, below, like we would have it here. Well, we just have to first do that. And that's just doing these swaps, but those swaps, they become little parallelograms that I just add in. So I just transform the order in which the splits appear here by doing these little swaps, adding in parallelograms, until I have above, 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 below, below. Then I have the situation, I just put in x2, and then I carry on. And by doing this, I get in the end my little split network. It really displays the splits that I had in my wiring diagram. So now I have to keep an eye on the watch. So again, those boxy things that we see, they should usually represent two splits that are incompatible, in the sense that if two things are compatible, that's the things that we see on a tree. Yeah, you don't get boxy things on a tree because all the splits are pairwise compatible. So a box in the split network should usually draw your attention because it is telling you, okay, two splits in my split system, they are incompatible. Now the thing that I get has boxes in it of splits that are compatible with each other, and I want to get rid of them because that's really annoying if you have boxes in there that are not corresponding to an incompatible pair of splits. Well, how can you do that? Well, sometimes it's easy. Well, there is this big bunch of boxy things in here, but in some sense, the things that go through, they are not too widely interacting with each other. I can't go into the details now what I mean by widely interacting, but in this situation, you can really just cut it off. The whole bunch of boxes can be cut away like here. Then everything's gone, and step by step, I will make my network smaller. In the end, I get a minimal one where I only have boxes for pairwise incompatible pairs. So here they interact more widely, those splits that go through. I mean, and one particular thing that I would like to point is that this one, S2 here, it goes up and somehow it crosses this split S and also this split S prime. The two splits, they are compatible, but they have a box in here. And there's another one, S2, that crosses S and it crosses also S prime. This is not so nice. And in this situation, well, I just can show you a little cartoon. I use these kind of flips that are well known. You can transform an unlabeled vertex, or the edges incident to it, into another one where you just make this little flip. It's just like looking at a cube and you go from foreground to the background and back. So you can just do this little flip. And with those little flips, you can just transform this thing step by step. Well, and either you can get to the situation that you get rid of those weirdly things going through, or if not, well, then you find another one that you can transform by little flips until it's gone, the whole gray thing. And step by step, if you have really carefully counted the white dots, they reduce by at least one every time you do it. So it really gets smaller. And at some stage, it's either gone, or it's the simple case where you can just cut it off. So in the end, you get a minimal network. It has, well, in the worst case, vertices and edges number that grows with a square of the number of splits, but usually the splits should not be that many, because otherwise you get a huge ball of things and you can't see anything. And the whole algorithm is polynomial. We didn't spend too much time getting it optimal or close to optimal with the runtime bound. This is really looking horrible, but in practice, it's not too bad. How much more time do you have?
I mean, if you want questions, you should stop now. If you don't want questions.
I think I'm almost done. Okay. It's just two examples. This is the same Oak-Galvos data set that we used, and we used this mapping of the taxa in the plane using one time the multidimensional scaling approach. Just take distance matrix, multidimensional scaling gives you a set of points in the plane, read out the splits, and then weight them. And of course, since in this example we even had geographic locations, well, we just used those points and again did the split system. This is just preliminary stuff, just trying out where, for example, the geographic information is still somehow contained in the distance matrix and how things look like that are not, when they are non-circular. Well, this kit can certainly be done, but this was all about drawing. I would like to thank my two collaborators, Vince and Bin, and also the funding agency that made it possible that we could continue our collaboration.
We have time for a question or two. No questions. Okay, well, thank you.